Greetings, AP Calculus AV students. Mr. Record here from Avon High School, and we are going to talk about a very important topic in advanced placement calculus. It falls under topic 3.3 from the new curriculum and exam description that came out in the summer of 2019. And this particular topic is all concerned about taking the derivative of an inverse function. This is a topic that isn't widely seen on the AP exam. Typically, you're going to see this perhaps as one multiple choice problem. If you basically can get your head wrapped around a formula or a relationship, the problem can be pretty easy. But nonetheless, it is a problem that many students do end up missing on the AP exam. Now, the purpose of this video is to run through 3 examples that sort of set the stage for the actual procedure that is probably best used on the exam. But I'd like to show these examples to my students so that they can understand why this particular derivative formula for derivatives of inverses exists in the first place. So what we're going to do here is we're going to break this down into what I call method 1, method 2, and method 3. And as I said before, we're going to talk briefly about method 1, and then we'll segue into method 2. And then once those videos are out of the way, I invite you to watch another one of my videos that will discuss the true method, method 3 that I call, the way that you would probably want to attack these questions on the advanced placement exam using this particular relationship. So these 3 examples, 4, 5, and then ultimately 6, will appear in a separate video altogether. So if we go back to the beginning, if I read the first example, and it says if f of x is equal to x squared, where x is either 0 or positive, find the derivative of the inverse of x at x equal 4. Now, I want to talk a little bit about the idea of the inverse. So for right now, if we take a look at this function f of x equal x squared, let's say that we were to graph that function. It's a very simple function. I'll create a new document here. I'm going to graph this on the TI Inspire CX2 CAS software, but this particular graph would render on virtually any graphing calculator, and that's what we have. Now, one thing about this particular graph that's very important is that it fails this very important test that we've perhaps learned in algebra. It's called the horizontal line test. If a horizontal line crosses this curve in more than one location, then we have a bit of a problem on our hands. That problem is that we cannot find the inverse of this entire function as it exists. And the reason that we cannot do that is because the definition of an inverse is going to basically render a graph that's symmetric around the line y equal x. Now, if a lot of that information kind of comes as a surprise to you, you might want to scour YouTube and maybe watch a video just over the basic ideas of the inverse function. But if I were to graph very quickly the curve y equal x, and I'm going to change that curve's attributes so that it'll be a slightly dotted line so it doesn't stand out so much. And then I'm going to go ahead and just change my window size here just a little bit as well. Let's go 4, 5, -1, and -1 will work. And then I'm going to quickly change these as well and have 1 all the way across. Now we can sort of see a little bit of daylight between the curve and the line to which it is supposed to be symmetric. Now, if we were to sort of reflect this line around this particular, or this curve, x squared around this line, what we would have would be sort of mimicked by what my cursor is doing on the screen. We would have a sideways opening parabola, and the issue that we have with that sideways opening parabola is that it is not a function. And we're really invested in trying to figure out the inverse function and then the inverse function's derivative. So if we're not a function, that's going to be a problem already. But fear not, because the problem knew better. And that is why this domain restriction x greater than or equal to 0 presents itself. So to do that in the graphing calculator, or at least the TI Inspire lines of calculators, I can just open this particular graph entry, and I can change the domain by adding a such that, that's control equals, and then in that particular such that bar, I will throw in x being greater than or equal to 0, at which point I will see only the part of the parabola that is indeed one-to-one, or passing the horizontal line test. That phrase one-to-one is another name that sort of is synonymous with passing the horizontal line test. And it's probably not a big mystery as to what the inverse of this function is. We're going to go ahead and figure it out anyway, because that's what method 1 is all about. Method 1 works only when it's very easy to generate the inverse function. Now, the problem with that, on the AP exam, you are probably never going to be in that situation. You're going to be dealing with functions that are either a little bit difficult to like solve for y once you interchange the variables, or more likely than not, you might be dealing with some values that are going to be extracted from a table. Now, in the case of step A here, it asks to find the inverse of the function by interchanging the x and the y and solving for the new y. So temporarily, that f of x is going to act as a y, but not for very long, because our first step is to actually interchange the variables. So let's say that we do that, and then upon doing that, we're going to solve for that y by taking the square root of both sides. Now, normally, algebra dictates that we have to put a plus or minus symbol right here. After all, we've just taken the square root of both sides of an equation. But because the domain restriction of the original function says that x must be greater than or equal to 0, that carries over to the y in the inverse having that same attribute. So if the y has to be positive, then there is no point in putting a negative sign in front of that square root. So as we get to this point, we have our inverse, and if we want to make this inverse just a little bit more fancier looking, we can use this very special notation, f inverse of x. F inverse of x is equal to the square root of x. Just a little side note here. This notation, this -1 superscript, you do not want to interpret that as, say, a reciprocal, as in like 1 over f of x to the first power. Unfortunately, in mathematics, we tend to run out of symbols, and we have to duplicate usage of symbols in completely different contexts. It's not too much unlike the English language, where we have words that are spelled alike and in some cases sound alike that might have two completely different meanings. So math is kind of the same in that regard. So this is going to be our inverse. So if I return back to our graph, I can go ahead and pull up the graph entry line, and my f3 of x function is going to be the square root of x. And we see that that guy is indeed nice and symmetric with respect to that line y equal x. And we're going to come back to this function and do something here with it in a second. In fact, I'm going to change the color of this function, make it a little bit bolder. Let's make that green. So if we return to the problem, the directions aren't just an algebra type of directive like find the inverse. It is to find the derivative of that inverse. Well, once we have this derivative equation, once we have this, inverse equation, finding its derivative is not too difficult. Now, from a notation standpoint, this might be new to you, but it's going to look a little something like this. We put the f inverse, and then we put the prime mark typically, and then we put the of x. Now, another way to say this would be the derivative of f inverse of x with respect to x. Either one of those would denote that we are about to take the derivative. And of course, the derivative of the square root of x is going to be 1/2 x to the -1/2 power, which can be rewritten as 1 over 2 square root of x. We're going to leave it like that. There is no point in really rationalizing a denominator. By the time you get to calculus, it's really not important, and it's kind of overrated. Now, specifically to this problem, to finish up, they want us to figure out what is the derivative specifically at the value x equal 4. So we are going to take that 4, and we are going to insert it for the x, just like we normally would. And upon doing so, we would get 1 over 2 times 2, which indeed is 1/4. And that is indeed going to be our answer. Now, because we've already done a lot of the dirty work and graphed this function, we might as well go ahead and just verify this particular result. So I'm going to return to my drawing here, and I'm going to use a very handy feature on the TI Inspire. Um, it will only work if you are working in a document. For those of you who are Inspire users, it cannot be done on the scratch pad, because we are going to go into the menu and we're going to access the geometry features. And one of the favorite features that I have in the points and lines is the tangent feature, option 8. And within that, it will actually compute the equation of the tangent line and show us what it looks like. And we're going to do so to the graph of the square root of x. And you can see that it's very dynamic. It'll actually compute it anywhere that we want. I want to see if I can put it right around here where the x is 1/4, or I'm sorry, where the x is 4. I'm going to plop it right there. That looks pretty good. And if I move this line up a little bit, we can see that the slope of that line that it just computed is indeed 1/4, and this certainly is the tangent line. I could extend those arrows if I wanted to kind of set it apart just a little bit, but I think we would all be in agreement that we have the correct tangent line. Let me move that back. All right, so at least we know that we have the correct answer. Now, like I said, method 1 is a little bit obsolete when it comes to the advanced placement test. In fact, even in my class, I don't give my students but maybe one problem where they can actually employ this first method. I say we're going to have to work a little bit harder. We're going to have to earn these derivatives. So we're going to move on to method 2. And it says that this method here is used when finding the inverse of the function is very difficult or perhaps even impossible. So you can see that the guidelines say to find the inverse function, and that's kind of a misnomer. It's not really necessarily a function per se. We have to kind of keep that in mind. We have to be kind of careful. So we're going to find that by interchanging the x and the y value. But it says here very specifically, do not solve for y. Well, there's a reason. And if we move right to example 2, and if we temporarily think of this f of x as the y, he's having a little dream about being y. And then if we swap the x and the y, we end up with this particular equation. X equal y cubed minus 4y squared plus 7y minus 1. Now, what we have to consider here is that the solving for y is next to impossible. It takes a whole lot more algebra than probably what I know in order to get this y by itself. But that's okay, because we still have the inverse computed. Solving for y is not a prerequisite for finding the inverse. Only swapping the x's for the y's is the prerequisite. So we go on to step B, and it tells us how to take care of that situation, and that is to take the derivative of y with respect to x implicitly. So you're going to take this derivative with respect to x, and on the left side that will give you a 1. The derivative of x with respect to x is 1. And then the derivative of the right side, if you use the chain rule correctly, would give you 3y squared dy over dx. Now, if you're bothered by that step, it's likely that maybe you need to look a little bit more at implicit differentiation. I have 2 or 3 videos, I think, on YouTube that deals with that, but there are several others that are quite appropriate to sort of brush up your skills on that particular topic. And we have the derivative of negative 4y squared, which would be minus 8y to the first, multiplied by dy over dx. And then lastly, the derivative of 7y is, of course, 7, but then we have to sort of tack on this dy over dx there as well. Now, we're going to continue by solving this equation for dy dx. And that requires a couple of steps. The first step is to factor out a dy over dx, which is going to produce 3y squared minus 8y plus 7. And then by the time you divide both sides by that mess that's attached to your dy dx, you have everything that you need. You have 1 divided by 3y squared minus 8y plus 7. Kind of fix that fraction a little bit. And unbeknownst to you, this is a very powerful discovery, because this is what's going to lead into the very important method 3 that we're going to discuss in a later video. But for right now, we need to finish this by evaluating this derivative at a very specific location. And as you can see, the problem says that we want to figure out where and what this derivative is at x equal 1. So the question becomes, what do we plug in for y? Do we plug in x equal 1? And the answer is no, because obviously an x is not the same as a y. We want to know what is this value of y when the value of x is a 1 once we've taken this inverse. So what that's going to force us to do is to take a look at our original inverse. That would be the one here in the first line, and we will solve that for y when the x is equivalent to 1. Now, if anybody's panicking about that, well, you should be, because I kind of am. That is not an easy equation to solve for. But luckily, if you look to the left, you see the calculator icon, which indicates that we are allowed to use a calculator for this problem. Now, there's a variety of ways that you can actually solve this, and I'm going to address my particular audience, my students, and we are going to use the TI Inspire, which is going to take into consideration some wonderful CAS features of the calculator, but it's not impossible to graph this on, say, a TI-84 and figure out what the answer is going to be. So what we're going to do in this particular case with our calculator is two things. I'm going to show you two different things here. So if I go to the calculator, and I'm going to just go to a scratch pad here, and I'm going to use the CAS feature of the calculator. I'm going to go into the menu, choose the algebra option, followed by the solve option, and I am going to physically type in that function. It was that equation, sorry, 1 equal y cubed minus 4y squared plus 7y minus 1. Now I have to tell the calculator which variable that it's going to solve for, comma y, and then when I hit enter, it will give me an answer, 0.349371. So I'm going to record that answer underneath here, 0.349371, and that will tell me at what value I would evaluate this particular y. So to get my final answer, all I need to do is take the derivative of y with respect to x, and then I can evaluate that such that either x equal 1, I could write x equal 1 down here, I could write y equal 0.349371. Either one is in essence the same thing, and again, I'm going to have to use the calculator to pull that off. So to do that, I'm going to return to the graphing calculator, and I am going to type in that particular expression. 1 over, and I believe we had 3y squared minus 8y plus 7. You know what's interesting? Did you guys look and see that that denominator, doesn't that seem to be the derivative of all that? That's interesting. That could be a great conversation for a future video. In any event, I'm going to go ahead and evaluate this such that, and a very neat strategy here so that you don't have to type in that long decimal, I can just simply go up, highlight it, and hit enter. I didn't really feel a need to store that decimal because I'm only going to use it one time here. And once I do so, I will get the answer that I'm looking for, 0.218 or 0.219 if you want to round. Either way will work. And that would close out example 2. All right. Now, I'm just going to briefly demonstrate the idea of example 3. And I might leave that maybe as an exercise for the viewers to take a look at on their own. But in this particular problem, it's a very similar situation. You have a function f of x, although it is in terms of a natural log and an exponential, but it is a calculator problem. So being able to swap the x and the y should be pretty easy, but the tricky thing is going to be evaluating the function when the x is going to be 3 and the y is 4. Okay? To return just briefly to example 2, if a student wanted to do this a little bit differently, it certainly can be solved by taking a graphical approach. And that graphical approach is kind of interesting in that a student with the CAS calculator or the TI Inspire on a graph screen would have to go into the graph entry and into the relation menu, because what we are typing in is indeed a relation. That equation that we worked with, 1 equal y cubed minus 4y squared plus 7y minus 1. Now, if I were to graph this, something interesting is about to happen. I get a horizontal line. I wonder what the y value of that horizontal line is going to be. Well, if we return to the solution that we found, it says the y in this equation is always going to be about 0.349. Compare that with the location of that, and it certainly seems like I'm going to have that ordered pair there. Now, I might be lucky and I might be able to go into my geometry page and my function, but I'm in a scratch pad, and unfortunately I can't access it unless I do a quick little save of this particular file, and I'm going to convert this to a document, at which point geometry does work. I can try to go into points, and let's try that again. Let's go into geometry, points. I'm a little bit more interested in the point on, and the point on that line, and if I lock that in right about there, it looks like that's what I want, isn't it? It looks like I have a y coordinate of 0.349, and that's going to be true anywhere where I have an x value, particularly at 1. If I can get it there, oh, not going to happen, not going to happen. I'm close, right? But anyhow, I'm going to be very, very close to that. Now, if I add more decimals to this, it seems like it's altered itself just a little bit, 0.37, and there's some reasons that that's happening. That's some anomalies with the calculator. It's kind of interesting. But for the most part, you can see that it's locked in at about 0.349. And if you remember, that's what we had in that particular instance. Okay? I suppose if you're using a TI-84, what you guys would need to do is to change these x's in this equation, or change these y's into x's, and then maybe subtract this 1 over, and then you would set your particular equation, which is now equal to 0. You would enter that as y1, and you would see where that graph crosses the x-axis. Anyhow, I hope this video helped. I encourage you again to take a look at example 3 and check out some of my other videos that will investigate method 3, which is a lot more prominently used on the AP calculus exam. All right, thanks for watching, and I'll see you next time.